Hi everyone, in this video we're going to be going over chapter 3.1, which is polynomial functions and their graphs. So from the previous video we know that our polynomial function of degree n is a function of the following form here. So our n is going to be a non-negative integer and our an is not equal to 0. The numbers a0, a1, a2, all the way to an are our coefficients. The number a0 is a constant term, so we don't have a x to a certain power attached to it. The number an is going to be the coefficient of the highest power, so this is going to be called our leading coefficient. And the xn, if the n is the highest power, then that's going to be our leading coefficient attached to it, the an. And the term, the whole term, an xn, is going to be called the leading term. So here we have an example of a polynomial. So I have 3x to the 5th plus 6x to the 4th minus 2x cubed plus x squared plus 7x minus 6. And move that forward because it looks like it's attached to it. Okay, so we have our coefficients here are 3, 6, -2, 1, 7, and -6. Our constant term is this -6 here. And then the leading coefficient is 3. And the leading term is 3x to the 5th, since that's the highest degree. So here's some more examples of some polynomials, the degree, their leading term, and their constant term. So for example, for 4x minus 7, it's a degree 1, because the x is to the first power. X squared plus x, our leading term is x squared, and 2x cubed minus 6x squared plus 10, our constant term is 10. Okay. So monomial is a polynomial of a single term. So that's just if it was just one of these terms here, if it was just one, or just this one, that's like a single term. So like x squared, x cubed, 3x, those are like single terms. So these are examples of something that are not polynomials. So we have -3 square root x plus 2x squared plus 5. If we were to change that, our x's, they would be to the 1/2 power, right? Because it's square root. So our exponent is not an integer, therefore it's not a polynomial. And then we have -3x to -2. This is also not a polynomial because we have a negative exponent and we want a non-negative integer. So here's some graphs of some well-known polynomials. So like we have our y equals x, x squared, x cubed, x to the 4th, and x to the 5th. So as you can see here, there's like some repeated patterns where x squared kind of looks like our x to the 4th, x cubed kind of looks like x to the 5th. And then also as our n, our exponent increases, the graph flattens out around the origin and it goes steeper elsewhere. So like x squared compared to x fourth. The x to the 4th is kind of a little bit more like this around the origin. Again, x to the 5th is a little flatter around the origin too. So here we're going to be learning about the end behavior of polynomial functions in a graph. So a graph of a polynomial function, we know it's continuous. And continuous means that it doesn't have breaks or holes, and it also has smooth curves. So polynomial graphs don't have corners or sharp points, or what we like to call cusps. For example, we have our graphs of a polynomial. So we have smooth, round curves on the left, and there's no holes. So on the right, these are not polynomials because we have holes here, we have a break here, and then this also isn't a polynomial. We have like sharp corners and then cusps. So the end behavior of a polynomial is a description of what happens as x becomes large in the positive or negative direction. So basically, what does the end, like up here, what does our end behavior look like here as x? Whoops. As our x gets bigger this way or this way. So what does this end look like in our end behavior? So to describe end behavior, we're going to use the following arrow notation. So x going to infinity, that's basically our x is increasing without bound. And as x goes to negative infinity, that means it decreases without bound. So although graphs may have intervals where it increases or decreases at some point, the graph will eventually rise or fall without bound. By moving really far left or really far right, it'll eventually kind of just like stop going all over the place, and it'll get pretty consistent. So our end behavior is determined by the term that contains the highest power of x. Because this is the case because when x is really, really big or getting really, really large, the other terms are pretty insignificant in size and don't really play a factor in the end behavior. So our end behavior are polynomials, or this is also called sometimes the leading coefficient test. So as x increases or decreases without bound, we have our polynomial eventually rises or falls, the f of x. So the end behavior is determined by the degree n. So by this, by degree n, and the sign of the leading coefficient an. So the bottom line is this chart here. So it depends if n is odd or even, and then also if an is greater than or less than 0. So this describes kind of the end behavior in like a short graph, but I'm going to go over my pictures first. So I have it split up into two cases, for n is odd and for when n is even. So let's look at when n's odd. If an is greater than 0, then the graph is going to fall to the left and rise to the right. If our an is less than 0, our graph rises to the left and falls to the right. So that's like here in this part of our chart on these ones. We have falling left, rising right, rising left, falling right. So now for n is even, if our an is greater than 0, it's going to rise left and rise right. If an is less than 0, we're going to fall left and fall right as well. So that's also this part of that graph. So this is a good short version to remember what we're going to do for our end behavior. So in this example, we're going to determine the end behavior of our polynomial. So we have f of x equals x cubed plus 3x squared minus x minus 3. So this is our leading coefficient, or our leading term, sorry, because 3 is the largest degree of n. So our leading coefficient is 1, and that's positive. And our degree is 3, which is odd. So we go ahead and look at our graph. So we go to the odd column, and then our an is greater than 0. So it's going to be this first one. So we're going to have it fall left and then rise to the right. And this is like a picture of that graph. So in other words, by falling left, that is denoted by y going to negative infinity. Rising right, that's like y going to infinity. And then this is like the left side. So this is like the falling and the rising, the y. Fall / rise is denoted by the y's. And then the left and right is denoted by our x's. So the left is as x goes to negative infinity, and then the right is as x goes to infinity. All right. So we're actually able to use end behavior to explain why some function, that's supposed to be some, to explain why some functions are appropriate models for only a limited amount of time. So for example, let's say that f of x is negative 49x cubed plus 86x squared and all that stuff. And so from this graph, we're able to see that the end behavior, since it's odd and our a is negative, that means we have odd a negative. So we're going to have that it rises to the left and falls to the right. So this is like saying as our x increases, the number of COVID cases will be negative, which we know will be positive. Which will be impossible. So we basically can't have a negative number of COVID cases because we would just have there would be no more COVID cases. So this is only, this model is appropriate only for a limited amount of time, basically. Okay, so we're able to use these zeros or solutions, which we have done in the past, but here's a more formalized approach to it, to graph polynomials. So if p is a polynomial function, then c is called a zero of p if p of c equals 0. So that's the solution to equation. So these statements are all going to be equivalent for real zeros of polynomials. So if p is a polynomial and c is a real number, then c is a 0 of p. So these are equivalent. X equals c is a solution of the equation p of x equals 0. X minus c is a factor of p of x, and c is an x-intercept of the graph of p. So those are all equivalent. So for example, we have p of x equals x squared plus x minus 6. So if we factored it, we would have p of x equals x minus 2 times x plus 3. So we know that if we set x minus 2 equals 0, x equals 2 is our 0, or one of our zeros. So we're just going to look at the x equals 2. So from what we just learned, we know 1, 2 is a 0 of p. 2, x equals c is a solution. So our x equals 2 is a solution of p of x equals 0. X minus 2 is a factor of p of x. And 2 is an x-intercept of the graph of p. Okay, now we're going to learn about the shape of the graph near a 0. So if c is a 0 of p, and the corresponding factor x minus c occurs exactly m times in the factorization of p, then we say that c is a 0 of multiplicity m. So let's go ahead and look at an example to just picture what that means. So we have f of x equals minus x squared, x minus 2 squared. So we know that our zeros in this case are when these equal 0. So basically this means that x equals 0 is a 0 and x equals 2 are zeros. So 0 and 2 are both zeros, and their multiplicity is 2. Because this term is to the second power. So it's multiplicity 2. So basically the 0 of 2, it's like it occurs like 2 times or m times. And then this one, it has a 2 or it's squared, so it also has multiplicity 2. Okay. So here we can look at the shape of the graph. So if c is a 0 of p of multiplicity m, then the shape of the graph of p near c is, and then this is our graphs. So here we have multiplicity of c, and I'm breaking it into odd and even. And so when m is odd, and then when m is even, in both cases we're going to have our m is greater than 1. And so because if our m was 1, then it would just be a line, right? Okay, so when we have m is odd, we're going to have it cross the x-axis at c. So here, our m is odd, c is r0, and we actually cross our line, or whatever kind of graph we have, it crosses the x-axis. If m is even, it's going to touch it and then turn around at c. So it's not going to cross the x-axis. Okay. Now we have the local maxima and minima of polynomials. So we've kind of seen that with like quadratic functions in the previous video when we found our vertex, and that was like our local maxima and minimum. So the point A of f of A is the highest point on a graph of M in some viewing rectangle. That's going to be our local maximum point. Our point B of f of B is the lowest point on the graph of F in some viewing rectangle when it's a local minimum. That means that's a local minimum point. So when we have our local maximum and minimum points on the graph of a function are called just local extrema. So local extrema could be a maxima or a minima in a graph. So here we have a graph example. So I have A of f of A, so that's our local max point because that's the highest point in the rectangle. And then I have B of f of B, which is the lowest point on the graph of F. And so that's going to be our local minimum. And so that's because it's kind of like when it comes to a point kind of thing. And that's when our values are going to be minimums or maximums. So local extrema of polynomials. So if p of x equals our polynomial, it is a polynomial of degree n, then the graph of p has at most n minus 1 local extrema. So here we have our p1 of x is that polynomial there, p2 of x is that polynomial, and p3 of x is that polynomial. So I just have the graphs there. I just did it like on Desmos and then just transferred it here. So our p of 1 of x has 2 local minimum and then 1 local max. So in total it has 3 local extrema. P2 of x, we have 2 local minimum and 2 local maximum. So we have 4 local extrema. And then P3 of x, we have 1 local max. So we have 1 local extrema. So let's apply what we just learned. So P1 of x, our highest degree is 4. So we could have at most n minus 1 local extrema. So we have 4 minus 1 equals 3. And yep, we have 3 local extrema. So that checks out. P2 of x, our x to the 5th, is our highest degree n. So we have 5 minus 1 equals 4. So we could have at most 4 local extrema. That checks out. And then our P3 of x, our highest degree is 4. So 4 minus 1 is 3. So we have at most 3 local extrema. So 1 checks out because it can't be more than 3. And 1's less than 3. Okay, so here are some steps on how to graph a polynomial function, just the different things that we need to keep in mind when we're graphing it and our different tools that we have available to us. So for step 1 is to use end behavior, which we could use to see if it rises left, if it falls right, or whatever. We look at zeros. So we find the x-intercept by setting f of x equal to 0. And then if we have an x-intercept at a point C as a result of like x minus c to some k multiplicity, So we could also look at our multiplicities to graph. So if our k is even, the graph touches and turns around. If k is odd, then the graph crosses the x-axis at C. And then if k is greater than 1, then we know our graph flattens out near that point C of 0. Okay, and then we could also use test points, test x points to see like what value of y we're going to get, if it's that's below the x-axis or if it's like above the x-axis, if we were also curious to doing this. Okay, and then we have our y-intercept. We're going to compute f of 0, and then we could also look at symmetry. So we could see if it has y-axis symmetry or origin symmetry. And then we could check if our graph is correct by using the maximum number of extrema or turning points of n-1 to make sure it's drawn correctly. So here, our example, we're going to graph f of x equals x to the 4th minus 2x squared plus 1. So our first step is we're going to look at end behavior. So we have our leading coefficient of 1 is positive and the degree 4 is even. So we're going to have that it rises to the left and rises to the right. Okay, now step 2, we could find our x-intercepts. So we have x to the 4th minus 2x squared plus 1 equals 0. So this was actually a problem that I gave you guys for extra credit for factoring or just solving an x to the 4th problem. So here I'm going to show you guys how to do it. So you use substitution basically. So we're going to have u squared equals x to the 4th because I want to change this into a quadratic function that I know how to factor. So if I have u squared equals x to the 4th, that means that I'm doing basically u squared is like in my x squared quadratic, our u squared is like our x. So then when I square that, that's going to be x squared in this case. Okay. And then my u is going to be x squared. So if my u is x squared, and then I square it, that's like squaring my u. So that's why u squared is equal to x to the 4th. Alright, so I'm going to use that substitution. So I have u squared minus 2u plus 1 equals 0. I'm going to factor, and I have u minus 1 equals 0. And then I'm going to go ahead and substitute my u's back in. So I have my x squared minus 1, x squared minus 1. And then I have difference of two squares. So I'm going to break each of these up. So I have x plus 1, x minus 1 equals 0. So that changes to x plus 1 squared times x minus 1 squared equals 0. So I set those both equal to 0, and I get x equals -1 and x equals 1. And so we know -1 and 1 are both repeated zeros, and they have multiplicity of 2 because they were squared. So there's an even multiplicity, which means that it's going to touch the x-axis at 1 and -1 and then turn around. So here's like the next part of our picture we've put together here. So this was like our endpoints, and now this is our x intercepts and multiplicities. Okay, so for our y-intercept, we have f of 0 equals 0 to the 4th minus 2 times 0 squared plus 1 equals 1. So we have a y-intercept at 0, 1. So I add that to the graph. And then our symmetry, we have f of x equals x to the 4th minus 2x squared plus 1. I test and I plug in -x, and I get x to the 4th minus 2x squared plus 1 back. Therefore, we have f of -x equals f of x, which means it's symmetric about the y-axis. And that's because it's even, right? We learned about even functions. Okay, and then our maximum number of turning points is 4, because that's our greatest degree. Minus 1 is 3. And that's true because we have 2 local mins and then a local max. So we have 3 turning points. Okay, here's another example where I'm going to sketch P of x equals x plus 2 times x minus 1 times x minus 3. And here it's already factored for us. So we know that our zeros are -2, 1, and 3. In this case, I'm going to go ahead and do this by intervals and doing test points. So my intervals with respect to my zeros are going to be -infinity to -2, -2 to 1, 1 to 3, and then 3 to infinity. So I split this up. So I have my different, so here I put my roots of -2, 1, and 3, and these are kind of like the intervals here. Okay, so for the -infinity, I'm going to put over here, and then like infinities over here. So I have my test point between -2 and -infinity is -3. So when I plug that in to my P of x, I get a negative. So I get my P of -3 is less than 0. That means that my y value is going to be below the x-axis from the interval -infinity to -2. And then between -2 to 1, I'm going to use the test point of -1. And then I plug that into P, so our P of -1 is greater than 0. So it's positive above the x-axis, our y values. And then the same thing for test points between 1 and 3, and 3 to infinity. So I'm going to be below x-axis and above the x-axis for those. Okay, so I have my my zeros are the blue dots I have on my graph, and then I just put my test points, which are the red dots. And so to connect them, I know that from -infinity to -2 this way, it's below the y-axis. So I'm starting here. And then my next interval is -2 to 1. And this is above the x-axis. So I'm going to connect those. And then I'm still above the x-axis here when I'm connecting those zeros. And then from 1 to 3, I'm below the x-axis. So I'm going here, and then here. And then from 3 to infinity, I'm above the x-axis. So that's that. Okay, so here's, it's called the intermediate value theorem for polynomials. So if f is a polynomial function with real coefficients, and if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c equals 0. So f of x equals 0 has at least one real root between a and b. So what this is saying is we have our a of f of a, and say that that is, our f of a here is negative, so it's less than 0. So here's our point. And then our f of b is greater than 0, so it's above here. So it's saying in order to go from being a negative y to a positive y, you have to cross the x-axis at some point. And we're saying that some point is f of c. And that means that we're going to have a root when f of c equals 0. So you're guaranteed to have at least one real root between a and b. So here we're going to show the polynomial function f of x equals x cubed minus 2x minus 5 has a real 0 between 2 and 3. So we're going to plug in 2 and 3 to find our f of a and f of b. So our f of 2, when we plug that in, we get -1. So that means that f of 2 is negative. When we plug in f of 3, we get 16. That means f of 3 is positive. So as f of 2 equals -1 and as f of 3 equals 16, the sign change shows that the function has a real 0 between 2 and 3. Okay, so that's our intermediate value theorem. And then here I just included a picture. I had this table just from previous math classes that I took, and I thought it would be fun. I thought it would be useful for you guys just to know like domains and ranges, and just these are pretty common functions that we deal with and graph in this course. So I hope you found that helpful, and we'll continue on next week. So this week we just had our midterm and review day, and so this is going to be the only video for this week, and then we'll continue on next week. So see you then.